All right, let's get started. So it's my pleasure today to introduce Céline Comte. Céline is a researcher at CNRS in the Computer Science Institute and Laboratory for Analysis and Architecture of Systems. She was previously at Nokia Bell Labs and Eindhoven University of Technology. Céline's research interests include stochastic networks, queuing, and reinforcement learning. She's the winner of the Telecom Paris PhD Thesis Award, and she's the organizer of many workshops and series in the applied probability community, including recently reinforcement learning for stochastic networks, and last year, this very SNAPP seminar series. So it's our pleasure to have Céline today to talk about routing optimization for asynchronous federated learning on heterogeneous resources. So Céline, please take it away.
Thank you. Thanks, Steve. And thanks all the organization team and scientific board of the SNAPP seminar for having me here today. And so as Steve announced, I will be talking about asynchronous federated learning, which is kind of a new topic for me. So I'm all the more happy to talk about it today and to share some of the results that we have in this area. So this is a joint work with Abdelkrim Alayan, who started his PhD last year under the supervision of Mathieu Juncker, who is also a co-author of this paper, and myself. And this is also a joint work with Eric Moulin from École Polytechnique. So in this presentation, and I will try to go through the following items. First, I will introduce you to the problem that we've been looking at, and I will try to give you, in case you don't know federated learning yet, a quick summary of what I understand, at least, of federated learning, and what it is also asynchronous federated learning. Then I will move on to the system, the particular algorithm that we've been studying, and the model that we used to study this. And then I will move on to questions about optimization of performance in these systems and looking at various performance metrics. So I should mention that this work has been submitted recently, and we are hoping to make it available on the archive soon. And I'm not feeling compelled to go through the end of the slides, especially because I know that they will be, if they are not yet available, online. And so please feel free to interrupt me if you have especially clarification questions. And also, Ziv, if you see questions in the chat, don't hesitate. Thanks. So, federated learning. So the idea of federated learning is to do a stochastic gradient descent in a decentralized way in order to learn the parameters of a model using multiple clients and a centralized server. So here a client will be, you can also see it as a server actually in some sense. A client is an entity in the system, an agent that has a local objective function. So client I will have objective function fi. And this objective function fi depends on the parameter w, which will be updated by the central server. And that will be used to parameterize a neural network. So let me quickly go through this notation. So agent or client I has a neural network which is parameterized by a parameter W. So this is what will be controlled by the central server. And this neural network, it takes an input X, and which can be a picture, for instance, and it will return a label. And the goal of agent I will be to minimize the error Li between the label predicted by the neural network and the true label. So we are in a supervised learning setting. The data set of image or input label pairs that are available at agent or client I is denoted by DI. And so the goal of agent I is to minimize the expectation of the loss Li average over the data set available at client I. So this is what client I has. And we also assume that client I is able to approximate the gradient nabla of Fi. with respect to the parameter W using a stochastic gradient estimate, which we will call GI of W. And the notation will be maybe a bit fuzzy, but hopefully it will be clear and it will simplify notation. Here, when I will say GI of W, I will mean some random estimate of the gradient of Fi. And possibly if I repeat GI of W multiple times, it will be independent estimates of the gradient. So hopefully it will be clear when we come to it. So this is what each agent I has, and the overall goal of the system is to minimize F of W, which is the average of the losses. So 1 over n, when n is the number of clients, times the sum of the individual losses. And here, just to make it clear, we don't assume that we are in an adversarial or adversarial setting. We really assume that the common goal of everyone is to minimize this average value F of W. So this is the general context in federated learning. So if we look at the history of federated learning, the first approaches they propose to take a synchronous approach, where time is divided in steps, and at each step, the central server sends gradient estimation tasks or requests to a subset of the clients. It waits until all of these clients have answered, and it updates the model parameter. So for instance, here, if we have just 3 clients, we can choose 2 randomly among them. So the central server has an initial value W0 of the parameter. Then it asks 2 clients, say clients 1 and 3, to compute a random estimate of their local gradient at this particular value of the parameter W0. And then it waits until both clients have replied, and it updates the parameter W1. And usually it will do it using a gradient descent algorithm. Once it has done this, it asks 2 other clients chosen at random to compute estimate of their gradient, this time at point W1, and so on and so on. And so this approach, it was already seen in the literature that it has in particular 2 limitations. So one is the straggler effect. So I think that many of you already know this one. This is the fact that you have to wait for the slowest client. So in general, it may take a lot of time to complete one step. And second one, which is somehow related, is that these synchronous updates, they require a lot of coordination for the central server. So due to these limitations, people introduced asynchronous federated learning, where in French, I would say that the server updates the model parameter au fil de l'eau, but in English, I would say as gradient updates are received. So now we assume that each client has a buffer or queue of requests. The central server can choose 2 of them uniformly at random to ask for a gradient estimate. And now if client 1 responds before client 3, the central server will immediately update the model parameter to make it equal to W1. And directly, it will send another request for a gradient estimate. And now, if client 3 replies with its estimate of the gradient taken at W0, the central server will make yet another update of the model parameter to make it W2 and send another request, and so on and so on. And so now, you solve the issue of stayness. It also requires less coordination among the agents, so it's more convenient when you have a large system. But now you may have other issues, and in particular, it was observed that it can be the estimate that you obtain eventually for the model parameter can be worse due to the fact that you use stale model parameters. So here, for instance, due to the fact that client 2 will send a gradient estimate based on parameter W1, even though the central server has already shifted to a parameter W2. And so I will show you some related work in one of the next slides, and we will see that there has been already a lot of work on this question, but there have been very few work that actually take into account the queuing dynamics in order to assess the impact of this gradient staleness. And so one thing that we do in this work is to model in a more precise way, in some sense, the queuing dynamics and to try to understand their impact on the performance. And so in particular, one conclusion that we will reach at the end is that what you have to do is to take into account two performance objectives that are sometimes antagonistic. One is to reduce the staleness of the gradients estimates, which we will see is measured by the mean relative delay. We'll introduce it later. And the other objective that you need to keep in mind is the speed of the system, because one of the points of introducing asynchronous federated learning is to not have to wait for everyone to complete in order to move faster. So this completes the general introduction about federated learning. I will give you more details on the model that we are actually looking at in this work in a few slides, but if you have any questions right now, don't hesitate. Okay, good. So as I was saying, there has been quite a lot of work on federated learning. And here I'm trying to give some overview of the literature. So a lot of people have worked on the introduction and preliminary works on federated learning. There have been also a few works that looked at identifying limitation of synchronous federated learning. And then there have been quite a few works that introduced various algorithms for asynchronous federated learning. This FedAsync, FedBuff, Async SGD, HashGrad, etc. And so here in this work, we will focus on one particular line of work. So the first one is Async SGD. So they propose some variant of asynchronous SGD, so similar to what I've presented. In a second work here about generalized async SGD from Comte et al., they proposed a generalized version of this algorithm where they allow servers to be sampled non-uniformly with the idea that it may perform better when you account for queuing dynamics and especially for heterogeneous service feeds at the servers. So I will actually come back to this work a lot later because we will look at this generalized async SGD algorithm and we will use similar modeling assumptions and some of their results to build on top of. And here I also mentioned a few recent works that try to analyze the performance of asynchronous federated learning. So there's actually this one in particular, which has Gauri Joshi as a co-author, and she was co-organizing the SNAPP seminar last year. I don't think she's anymore this year, but this one I saw it just a few days ago, so I haven't had the time to look at it in details, but I think it's also interesting in this context. Okay, so our work in this context, so we first start off from these results, and especially a bound on performance derived from by Lecomte et al. We build up on this and derive more explicit expressions for some of the metrics they look at. And we also propose a gradient descent scheme to optimize performance and especially to choose a routing probability vector that minimizes their upper bound. So this is in order to optimize one performance goal, which has been studied a lot in the literature, which is the time average of the square of the norm of the gradient of the objective function. We find that this is useful in some contexts, but as we'll see in the numerical results, there are contexts where it may not be desirable actually to optimize this performance objective. So in the second time, we introduce an alternative performance objective, which we think in some cases may yield better performance. And so we also propose an upper bound for this other performance objective. And we propose also a gradient descent scheme to optimize this other upper bound. And finally, we numerically evaluate the performance of all of these on multiple image classification tasks. So the precise model that we look at, as I mentioned, it's called generalized async SGD. And on the left, we have what is done by the central server. On the right, what is done by the client. So the central server, let me quickly go through it, and then I will give a bit more detail. So first, when it initializes the system, it chooses a parameter W0, possibly randomly, and then it will send a number M of tasks, of gradient estimation tasks to the client based on W0. So this is what we were doing in a previous slide with asking clients 1 and 3 to compute gradients estimates based on W0. And then it will enter a for loop, and at each time, it will receive a stochastic gradient from a client CT. And here, this is CT, this is whichever client completes its gradient estimate first after the previous one. So this is dependent on the dynamics of the system. So using this gradient estimate returned by client CT, the central server will update the parameter. Then it will choose on line 6 a new client to which it will send the current value of the model. And then it will send the new model parameter to this client. So here, PI, this is a state-independent routing probability that we choose, and this is one of the parameters that we'll study. And it's also worth mentioning that here, the gradient estimate GCT returned by client CT, it's a function of the model parameter WIT, where IT was the model parameter at the moment where the request was sent to client CT. So when the central server decided to ask client CT to compute this gradient estimate. And so on the other hand, we have the clients. So each client I has a queue of tasks and a local data set DI. And whenever the queue of client I is non-empty, it will take the received parameter W from its queue in FIFO order, so the oldest one. It computes the gradient estimate GI of W, and it sends the gradient estimate to the central server. And so here again, this W, this is the value of the model parameter at the time, so possibly a while ago, at the time when the central server sent the gradient estimate request. So what we'll see in our assumptions is that, so our critical assumption is that the only operation that takes a lot of time is this computation of the gradient estimate GI. So this is an assumption. It may hold in some context, maybe not in other. For instance, when there's a lot of a long communication time between the client and the central server. But this is what we assumed here. And we also assume that the parameter update from the central server, which is just an addition, is also takes no time. So the only thing that really takes time is the gradient estimation. So more specifically, so maybe I will start actually with the second part of the slides, since this is what I was talking about. We assume that each client processes the tasks in its queue in FIFO order. The processing times at client I are IID exponentially distributed with a positive rate mu I, and we neglect the processing times at the central server and the communication times. So this is what will define the actual dynamics of the system. And on the other hand, we also have assumptions on the data sets and the functions under consideration. In particular, we assume that so the function f is bounded from below. Each function fi has a L-Lipschitz continuous gradient. And these two assumptions say essentially that the gradient estimates GI are reasonably close to the gradient of f. And I should mention that these assumptions are quite common, especially in the two works that I mentioned from Lecomte and the previous one on async SGD. These are similar assumptions. I will finally introduce some notation that will be useful for later. So some of it was already considered before. So here at each step t, so by a step, I will mean one period of time between two consecutive model parameter updates. So during a step t, a first task is assigned to a client AT, and client I is chosen with probability PI. Then a task is next completed at client CT, and the conditional distribution of CT given the history is now completely determined by the fact that the service times are exponentially distributed. So you can write it down explicitly. And we will call x n-1t the vector that gives the number of tasks at each client at the end of step t. So xit is xit minus 1 plus 1 if client I was assigned a task, and minus 1 if client I completed the task. I write this m-1 to emphasize the fact that here we look at the state right after a task completion. So the sum of the xit over I will be m-1 and not m. So that's will just make things easier for stating the results later. Another element that we need to define and that will be important is the relative delay. So let me first introduce RIT. So it may not be obvious from this definition here, but RIT is the remaining time of the task which has been most recently assigned to client I at time t. And this time is not counted in absolute time, but in number of model parameter updates. So it counts the amount of time until the completion of the most recently assigned task at client I in terms of the number of times the model will be updated. So this is for RIT, and now DIT is exactly almost the same. It's RIT multiplied by an indicator function that says whether we actually had a task assigned to client I at time t. So DIT, this is what we will call the relative delay. And so it will be equal to 0 if no task is assigned to client I at time t. And it is equal to the relative delay of this task if the task is assigned to client I. Lastly, we assume that the Markov chain xt is stationary, so we will drop the time t indices, and I will quickly come back to it in the next section because we'll see what this stationary distribution is. Okay, so this is for the long introduction of the context and the model. And now I move to the preliminary results that we'll use then to our first main contribution. So in this work from Le Comte et al., they observe that the dynamics of this system and of this xt are given by a Jackson network. So I think many of you will know what a Jackson network is. This is a queuing network which has a very nice stationary distribution, which has a product form. And so you can compute it explicitly. There are sometimes challenges in computing the normalizing constant of this distribution, but there are also algorithms that allow you to compute it. And here it's more specifically a closed Jackson network, which has, so the servers of the Jackson network are the clients and the central server. And the clients of the Jackson network are the tasks of the federated learning system. So this is their first main observation, and another result that they had, which we will rely on, is an upper bound on the empirical mean of the norm square of the gradient of f. So let me go through it. So here they look at 1 over big T, where big T is some time horizon, times the sum of the expected value of the square of the norm of the gradient of f taken at the successive values of the parameters Wt. And so they have an upper bound, which is G, and G, so it's written on the line below, it's given as a sum of 3 terms. So the first term, it will usually tend to 0 as t goes to infinity. The 2 other terms, they will not in general. So the first term, it's common in this type of works, even without looking at decentralized federated learning. And the A will depend on the initialization and the distance you have to go through in order to reach a minimum. And so it's divided by t plus 1. Then the second term, it depends on 2 variables. So eta is the step size and the number of clients. L and B depend on the problem. L is the constant, the Lipschitz constant, and B depends on the heterogeneity of the data sets at the client. The third term is what we will be especially interested in, because here you can see that it involves the expectation of the relative delay, which we will be able to compute using the Jackson network dynamics. So I think there are many things that can be said about this upper bound. Here we chose to focus on m, the number of tasks, and p, the routing vector. But for instance, you could observe that the step size, eta, it will have very different impacts on the three terms in the sum. And so it can also be an interesting element to discuss. Something else that I wanted to mention is that this is this is an interesting theoretical result. In practice, there are a lot of constants that we can only estimate heuristically. And so in the numerical results, especially, we will actually estimate them empirically, or we will assume that they have a specific value. And so we won't focus too much on that, but this can also definitely be an interesting question. So our first result is actually to compute this expectation of di. And as I already hinted before, di is the relative delay. So you can actually compute it using a variant of Little's law. So we couldn't find an exact statement of Little's law that matched this particular setting, so we proved it. But that's really Little's law. And so the idea is that you look at the system in discrete time. And because di counts the number of CS steps or of steps or service completions. And so similarly, you look at the expected QNet, but count it at discrete completion times. So this is the main idea, but otherwise this is really close to Little's law. So this is the first part of the result. The other part is an expression for the gradient of this delay with respect to P. And for this, you can actually directly use a closed form expression for the stationary distribution to derive this expression that I'm showing here. And this actually holds more generally for such type of closed form distributions. The nice consequence of this expression is that one, you can compute actually, look here, you can actually compute these expressions in closed form if you know the parameters of the system, in particular the service speeds of the servers of the clients and the routing probability. But if you don't know these parameters and you need to estimate the gradient empirically, this is also a very convenient expression because it only involves the current stationary distribution and not anything else. So here, this is for the detail. So if you want to compute these two expressions on the top, you need to compute the expected value of some xi and the expectation of the product xi xj. And you can compute these two using these expressions that involve some constant z and m, which are the normalizing constant of the junction network and which you can compute using very classical algorithms like Poisson's algorithm. So with this, you are actually able to compute the gradient of the expectation of di. From this, you can compute the gradient of the upper bound g with respect to the routing probabilities. And so using this, you can apply a gradient descent to find optimal routing probability vector P. So of course, this is a gradient descent, so you will fall on a local minimum. But here in the numerical results that I will show, this is what we've been doing, and we observed that it was working quite well in practice. So a few consequences of this result. So first, since expectation of di is equal to expectation of xi, you know that the sum over I of the expectations of di are equal to n-1. And and you can also argue that the expectation of di is an increasing function of n, the number of tasks. And so it leads to the conclusion that the best at least to minimize G, the best you can do is to have only n equals 1 task circulating in the system, which can sound counterintuitive a priori, because with n equals 1 task, actually you're almost back to the synchronous federated learning setting, where you always wait before updating the model. But it's actually intuitive in the sense that if I go back to the performance metric that I'm looking at here, the only goal is to minimize the average of the gradient errors over the updates. But it doesn't account at all for the time it actually takes to make these updates. And if you forget about the time it takes to make these updates, then indeed the thing that you want to do is only to minimize the stayness of the gradient, and so to minimize the number of tasks that circulate in the network. This is our intuition for this. And if we look now at the dependency of G with respect to the routing probabilities, so you can show that the first term doesn't depend on these routing probabilities. The second term depends on them and is actually minimized by taking a uniform routing vector. And the third term is actually the most interesting one, because it turns out to be non-monotonic with respect to the routing probabilities. Here on the right, I show a case where I only have 2 clients and 20 tasks. And so I have a slow client and a fast client. And we show in the y-axis the value of this sum, just this part. Oh, sorry. Just this part with respect as a function of the routing probability P to the slowest client. So we can see that we have 2 local minima here. One of them is also a global minimum. And it shows that in this particular case, the best thing to do in order to minimize the third term is to send almost all the traffic to the slowest client. And our intuition for that is that since you know that the sum of the related delays will always be equal to n-1, if you fix n, the best you can do is to kind of slow down the system and always or almost always choose the slowest server, so that in some sense everything works at the speed of this server. At least this is my intuition for this. With this expression, sorry. With this expression, we can also derive explicitly the bound G for 2 particular routing probability vectors, P uniform and P proportional to mu. So explicitly up to these constants that we mentioned earlier. And we thought these 2 routing vectors were interesting. The first one is the one that has been studied a lot in the literature. And the second one, proportional to mu, is one that is often used in load balancing. At least it feels quite natural in load balancing to try to equalize the load between the clients. So now we move to some numerical results. So for this particular setting, we considered 2 different types of distribution of dataset heterogeneity between the clients. One which is reasonably homogeneous, and another one which is more heterogeneous across clients. We can actually, we did look at cases where we had very extreme heterogeneity between the clients. This is also given in the paper, so once it will be available, you can also take a look at that if you're interested. So the procedure we follow to plot the numerical results is that first we try to optimize the upper bound G using the Adam gradient descent algorithm initialized with P uniform and using the gradient expression that we gave earlier. This gives us a P star, which is a minimizer of the bound G. And then, so for this P star, for P uniform, and for P proportional to mu, we simulate the dynamics of the Jackson network, which will give us the dynamics of our system. And we evaluate the performance of the generalized async HGD in this system on 2 image classification tasks. So this is how we derived these numerical results. Here, the first row is the accuracy, the second row is the loss. On the left half, we have a homogeneous data set. On the right half, we have heterogeneous data sets. And as I said, we compare 3 routing vectors. Green is the optimized routing. Red is the uniform one, and blue is the balanced or proportional to mu. And so what these results suggest is that in this scenario, the optimized routing gives a higher accuracy and lower loss, so better performance than these 2 previously existing routing vectors. Here, I should mention a few things. So we have reasonably different speeds between servers, between clients. So we have 20 clients, and the fastest one is 20% faster than the slowest one. So that's heterogeneous, but not so heterogeneous. And we also chose a scenario where the number of tasks is large compared to the number of clients. This is actually a scenario that exacerbates the difference between the optimized routing and the uniform and balanced routing. When you have less, fewer tasks, the difference is also smaller between the 2. One last remark that I should do is that here in the x-axis, we plotted what we call CS steps. So that's the time steps as defined in the model, so the parameter updates. But this is not the physical time or clock time. And if we did plot the clock time, the performance of the uniform routing and the optimized routing would actually be reversed, because the optimized routing, it makes better updates per model parameter updates by actually slowing down the system. And we found out that in this particular case, it actually chooses the slowest server more than 40% of the time. So PI, where I is the slowest server, is slightly above 40%. So that's extremely large. Okay, so this is the end of this first part about optimizing these metrics. And consistently, in the second part, we actually consider another metric that does account for the clock time. And so here, let me walk you through it. So here, the performance goal that I'm now considering is still 1/t times the sum of the square of the norm of the gradient. But this time, I multiply by tau t, where tau t is the duration of step t. So that's the amount of time between the 2 successive parameter updates. So you cannot see it exactly as an average over time, because if you wanted to average over time, you would divide by some big tau, which would be the total duration of the simulation. Here you really divide by the number of model parameter updates. And in some sense, this allows you to see this tau t, the duration of the update of the step, as some kind of cost that you also want to minimize. So this is how we include physical time into the computations. And so here we derive another upper bound h, which can be seen as the counterpart of g, which has again 3 terms, where one term depends on how you initialize the parameter. Another term depends also on the heterogeneity of the data sets. And the last term depends on something which is the counterpart of the delay. But this time, so there are a few differences. One is that now you have this lambda of p, which appears in all 3 terms. And this is the throughput of the system. So that's the expected number of updates that are done per time unit. And also here, before we had this expectation of the related delay, which was xim minus 1. Now, since we consider some continuous time, we actually use the expectation of xim because we look at the system in continuous time. And well, most of the time, in continuous time, there are m tasks dispatched at the client. So this is a quick description of this bound. And this throughput lambda of p, it can again be computing using these z constants, which are the normalizing constants, and which can be computed using Bosen's algorithm. So I should mention that shortly before this presentation, we found a glitch in the proof. So this is why this is written as a conjecture. So we hope to fix it. And I think our current assumption is that in order to fix it, we may need to change a little bit the lambda of p that appear in the first 2 terms. This would be not exactly lambda of p, it's something which is very close to lambda of p. So we will see to fix that. And the numerical results that I will show, they actually rely on this bound h, and you will see that it also actually gives quite a good performance in terms of minimizes the left-hand side of the bound. So this is at least an empirical support for this conjecture. Quick discussion. A lot of the conclusions that we drew for G also hold for H. And in particular, for instance, here on the 3rd term, you know that the sum of the xim is m. So you know that if you reduce one of them, you will actually need to increase the other one in return. So that's a trade-off you still need to find. The big difference between G and H is that H is no longer an increasing function of M because it accounts for the duration of the steps. And so in particular, if you fix the routing probability vector P, you will have some M star, which in general is larger than 1, that will minimize the upper bound H. On the right, we plotted this upper bound H for a uniform routing vector as a function of the number of tasks and for different value of the step size. And we see that indeed it has a minimum which is strictly larger than 1. And that this minimum seems to decrease with the learning rate, actually. So I will now go to the numerical results, and then I am at the end of the presentation. So we use a similar setting for the data sets, similar procedure for optimization and simulation. The difference now is that we try to minimize the H bound instead of the G bound. And these are the numerical results we obtain. This time we have the clock time, like physical time in the x-axis. And in the y-axis, we again have the accuracy and loss. And we compare with the uniform routing. And we see that in this case, the optimized routing does perform better than the uniform routing in clock time. So this leads me to the conclusion of this talk. In this talk, we studied a model of an asynchronous federated learning system. We proposed in particular an alternative performance metric, which we think is relevant in some applications. And as future works, I think that you probably observe that this model and many models actually make a lot of simplifying assumptions and put a lot of restrictions on the dynamics and on some parameters. So for instance, I think a lot of the issue, for instance, is due to the fact that each client processes its tasks in its queue in first come, first served order. But for instance, if it naively always took the most recent one, maybe you would get a better performance, but I don't know if that's doable in practice. So this is, for instance, one question that could be considered. Also, you could naturally think of doing state-dependent routing, which would be like more parameters to optimize, but maybe better performance. So these are questions that we can look at. You can take a look at the references that I gave in the talk, and thank you for your attention.
All right, thank you, Céline. Let's give Céline a round of virtual applause. So any questions?
There's an applause. Positive.
Okay, I have a question. So, okay, the first question I had is, you said there was something that was basically Little's law, but it didn't quite work.
Okay.
Can you explain? I'm curious to hear about that again.
Yeah, sure.
Sounds awesome.
So at least usually when you apply Little's work in Jackson networks, you say, so expected queue length is throughput times mean delay. And so this is usually expressed in continuous time, meaning that the mean queue length is the mean queue length over time. And similarly, the mean delay is counted in what I called clock time throughout the presentation.
Sure.
Here, we did it slightly differently because we didn't want to look at the continuous time delay. We wanted to compute the delay counted in number of service completions. And so if you write it down and take a look at the dynamics, this is still really almost Little's law, but you need to write everything in discrete time. And the important thing is that possibly that's the time looked at, the system looked at completion times. So possibly there will be a random amount of time that will occur between two consecutive observation times, but this you can ignore actually. So that was what I meant.
Great, thanks. That makes sense. Okay, we also have a question in chat from Jiayu about whether you found the optimal pi.
So the optimal routing vector, I'm not sure, because basically what we did was to try a lot of different, I think at some point we tried different initialization points, but yeah, I don't have guarantee. I think that we actually reached the optimal.
I see. And if I remember correctly, at least your numerical examples, so you get a complicated bound, right? And you can numerically optimize that bound, but you're still numerically optimizing a bound and not the real.
Yes, absolutely,
thing.
yes. Also.
Okay. But I guess the empirical performance shows that that's still a good idea.
Yeah.
Great. Okay, any other questions? All right. Well, let's thanks Céline one more time. And then so this has been the penultimate SNAPP seminar. Thanks everyone for attending. The last seminar of, sorry, I should say last seminar of the semester will be on Monday, December 9th at the usual 11:30 a.m. Eastern Time, and it will be given by Dan Lacker. So see you on December 9th. Bye, everyone.